I'm going to talk about fairness in networks. It's really not a new subject, it's an old subject. And you might think because I'm getting on in years, it's the only thing I can keep saying over and over again. And it does tend to be a bit of a hobby horse. It's a mission I've given myself to get this idea accepted. So I'm going to try and convince you that we should be fair to flows. And this title was just a play on the word fair, which means a lot of different things in English. It means attractive, it means trustworthy, and it means something between good and bad. Fair on your school report is not really a good thing. But anyway, I'm going to try and convince you that this is still relevant, and it's relevant in particular now because there's a lot of activity at IETF and in research on networking on the subject of active queue management, AQM, and congestion control. And this has arisen recently because of activity in two areas in particular. That's the home network, where there's the phenomenon of bufferbloat, which I guess you've been exposed to because there's been a proponent, Dave Tartt, was here at Links for a time. And the second environment is the data center, where there's lots of activity on networking in data center, interconnecting servers. So there's a new IETF working group on AQM, and they've given themselves the mission of defining new AQM or recommending AQMs which do these things, which were the aims of AQM when it was only red, and people have looked at different ways of doing this. And it's impossible to look at AQM without also thinking about congestion control, because the user's end system protocol like TCP is going to react to congestion signals provided by AQM, and it's got to recognize that, especially now, that there's not just a TCP anymore, that there are lots of different versions of TCP, in particular high-speed TCP. There are also new application level transport protocols which are sharing bandwidth dynamically under the impact of the AQM. So that's a pretty hard task, actually, and I think it's impossible. So I think this is not the right way to do things. I think you should really give up on this. This is so silly. How can you continue to rely on users or terminals implementing a congestion control, which is going to be very nice to everyone else and very polite? It just doesn't seem reasonable, and I don't believe it is. Instead, as I said right at the start, we should impose fairness in the network, decouple sharing and rate control. And I'm going to argue that doing fairness in the network is feasible, is scalable, and is sufficient. It's not sufficient at the edge, and I'll say a few words about that at the end, that you need something a little bit more complicated. Pure fairness is not sufficient. You've got to take account of particular user requirements and different characteristics of traffic in the edge. So that was the brief introduction, and now this is the outline. So I'm going to first recall the problems we're experiencing in these areas, bufferbloat and data centers, and then make my case for fair queuing. So first of all, bufferbloat. So bufferbloat, you may have learned this word bloat to bloat. It's an English word which is not very current. It means to get bigger, excessively bigger. So old people get bigger, typically. And the problem is that the thing which is getting bigger in home networks is the buffer in the gateway. So the buffer is getting bigger, and that's not very good for congestion control, as I'll explain. So this is a router, home router typically, with a buffer, a TCP flow, and you know that the TCP flow rate by the window control protocol does these zigzags, and as a function of these zigzags in rate, the queue fills up, there's a loss, TCP reacts and it decreases and so on, so you get this sawtooth. So this is a natural use of the buffer for carrying a TCP flow with 100% throughput, using the link fully. And this kind of queue has been called good queue in the bufferbloat world, as opposed to what you get when the buffer gets bloated. So the buffer gets bloated, you still have the zigzags, but instead of occurring at the bottom end of the buffer, they're occurring at the top end. So the buffer's going to fill up, and you're going to do the zigzagging bit, the sawtooth bit, at the top. So you've got a permanent queue, which is called a bad queue by the bufferbloat. So this is introducing latency, which is useless. You're gaining the throughput, you're saturating the link, which is okay, but you're introducing latency. And that's not too bad for a TCP flow, but when you use the same link for carrying real-time traffic, like a voice VoIP flow, then these packets, these green packets, are going to encounter this fat buffer full, and they're going to incur latency. Useless latency, which can be excessive because these buffers are getting very, very big. A secondary issue, which is not really addressed by bufferbloat, is fairness. We can, as I said, have different TCP versions. You can have just the same TCP versions with different round-trip times, making one more aggressive than the other, so that the sharing of the link tends to be unfair. This is the packets in buffer will be proportional to the bit rate on the link. And in particular, if you had any unresponsive flow, that would be particularly bad. So this is perhaps a different problem to bufferbloat, which one problem which is addressed in particular by fairness. So in this recent research on bufferbloat, there have been new AQMs proposed. In particular, these two, Codel, proposed by Kathy Nichols and Van Jacobson, and PIE is proposed by people from Cisco, Ron Pang and others. And they're both trying to work on the delay rather than on the loss, so that they will not saturate this big buffer, but rather they'll tend to try and provoke a congestion indication before the buffer gets too full. So they're quite clever, they do clever things. There's some debate which is better and so on, which is not settled. Obviously, they don't do anything about fairness. They're typically not intending to make sharing fair, and they're incapable, as far as I can see, to realize fair sharing if there are aggressive flows in competition with polite flows, which will reduce their rate. What's more interesting from my point of view is the more recent, after these two propositions, the more recent proposal to combine AQM with fair queuing. So these home routers are often based on Linux, and Linux has got in the kernel a fair queuing algorithm. It's called stochastic fairness queuing, and it does very close approximation to fair queuing anyway. Using these algorithms, it's using basically deficit round robin, which is a well-known algorithm. And FQ Codel has adopted that algorithm, but rather improved it somewhat by at least these two enhancements. One particular enhancement is interesting in that it's possible in this SFQ algorithm to recognize flows which are already got a backlog and packets which arrive to flows which don't have a backlog. And FQ Codel will give priority to the latter packets, packets arriving to a flow which doesn't have a backlog. Such flows typically have a low rate. Because they have a low rate, they don't have a backlog. So you're going to give priority by this mechanism to the packets of flows of relatively low rate. So that includes flows like voice over IP or streaming video, typically. So you're giving implicit priority to that kind of flow. You're improving their latency without impacting the throughput given to the kind of bulk data flows using TCP. And then you also have a different drop protocol, drop mechanism, which is more efficient. And Van Jacobson, a guru, has said that this is great. So now it's great, obviously. Even though Van was proposing Codel, he recognizes that using fair queuing is a really good idea. So that's kind of a stamp of approval on fairness in this particular environment. Yeah?
Quick question, but I mean, most of the video flows at the moment are basically TCP. Because they are embedded over an HTTP connection that runs...
Yeah, they come in bursts. Yeah, that's different, yeah.
How this would help those? Or would...
It wouldn't help them. I mean, your burst will go through more or less like a TCP burst. And that's not a problem because you're sending a burst in advance of when you actually use it. So I don't think it's a problem. Yeah.
One of the other words that people always use when they talk about this stuff is priority, and you haven't used that. Do you believe in it, or?
I think it's necessary in the access in this particular environment, and I'll explain that right at the end. But in the core of the network on big shared links, it's not necessary.
And the other thing is your diagrams with the waves. So those assume that there's a static channel that's available.
Yeah.
And is that realistic?
Well, it's realistic for some types of access, yeah. Some types of access are shared, but no, that's not the huge issue. The huge issue is how you share the bandwidth you're available, even that bandwidth is sharing, is varying. But this is a simple introduction. I'm not covering all buffer bloat and all problems in the access, okay? What's interesting is to understand how fair queuing is realized using the SFQ scheduler in Linux, and is also could be implemented in shared buffer switches or routers. So the idea is that you'd have all your packets stored in RAM, and you'd have some queue logic which tells which order you're going to fetch these packets from the RAM. And that consists of an enqueue process which will put your packet in the RAM and put a pointer to that packet in a queue related to that flow. In fact, it's not a queue, but it's just going to be a linked list, a data structure which can tell you in arrival order the packets of blue flow which are waiting. And then the dequeue logic is going to cycle around these different queues. It's going to pick one which is at the head of the cycle at a particular time, and it's going to take the head of this FIFO list and fetch the packet from the RAM and transmit it. So it's not a very complicated scheduler, and its feasibility depends to a large extent how many of these lists, I won't say queues because they're not really queues, they're lists of packets, how many of those you need to manage. And that's going to depend on how many flows are active at a given instant in time. And by active, I mean they've got a packet in the buffer, at least one packet in the buffer. We'll come back to that notion of active flows and complexity of fair queuing later. So now the second area where there's interest in new AQMs, new congestion controls, is the data center. So the data center, very simply, succinctly, is typically like this. You've got lots of servers arranged in racks, 20 to 40 servers in a rack. They have a top of rack switch, which allows communications within the rack and communications to other racks via some aggregation switches. So 2 layers of switches, and then some routers at a higher layer, which will interact pods, groups of racks of servers, and the internet. Okay, so it's just an interconnection network here. And the traffic in a data center obviously is very varied depending on the applications, but typically we can recognize that there are some bulk data transfers, transferring chunks of data, high speed, from server to server for whatever reason. For some map reduce, you've got to fetch some data to do your mapping on it. And then there are query flows. So query flows are just maybe coming from the web. You want a response to a query, and this is going to lead to lots of activity in the network, but that's got to be done very quickly. So there's a combination, as is typically most networks, of a requirement for high throughput and low latency for different types of flows. And it's observed that this doesn't occur very well. I mean, I'm getting ahead of myself. What I wanted to say was we had this idea here. We have a switch here, which has got a buffer, like the home router we talked about in bufferbloat, and we were interested in sharing the buffer and sharing the links which this buffer serves between flows, between links and flows going to different links. And it's a shared buffer for all the different links served by the switch. This is a common architecture for an Ethernet switch. And we have these different types of flows, and that's the observation I wanted to make, that that TCP doesn't work too well. That TCP is going to saturate the buffer on the bulk transfers, and then when you get a query flow, which wants to go through very quickly, it gets stuck behind this traffic jam of bulk data. And that's pretty bad. So the people have been working on how to deal with this, and they've been inventing new congestion controls, new TCPs, yet more new TCPs. Data center TCP was perhaps one of the first to attract a lot of attention. This is from a team at Stanford, around Balaji Prabhakar and others. I won't go into the details because I can't remember them. Basically, it's trying to do the delay base. It's going to send explicit congestion notification signals before the buffer saturates, and have the TCP control algorithm in the end system, in the server, reacting in a particular way. So it's not too different from TCP, but it's basically better. And obviously they prove that this is much better than TCP. But it couldn't have been that good, because then there were other proposals which have come along in SIGCOMs, NSDIs, and different conferences since then. So I'm not going to go through the details of all these. It's just interesting to note that the team which invented the first one has invented the last one here. So they obviously proved that it works super, and then they find perhaps it didn't work so well. And I believe it's not so easy to imagine a new TCP protocol, even assuming, as they do, that all the flows, all the applications within the data center are doing the right thing. They're all implementing DC-TCP, or they're all implementing Hull, which is perhaps reasonable in a data center like Google private data center, where you can control that, but it's certainly not in a public data center where transport protocols are part of the virtual machine software and whatever. What came along, which is very interesting, is a new proposition in last year's SIGCOM, from, again, same team. This team, in fact, is including people you'll have heard of, like Scott Schenker and Nick McEwen, Sachin Kati. So these are typical SIGCOM heroes. And Mohamed Alizadeh, who's the author of the 3 papers as a PhD student. So they've come to the conclusion in this paper that TCP, or new TCP, is not the answer. That the answer is to decouple flow scheduling from rate control. So don't rely on TCP to do the sharing. Don't rely on TCP to ensure low latency for the query flows. Do scheduling. Do scheduling in servers and in the end switch. So the idea is you've got a flow going from a red server to a green server via the interconnection network. What they're supposing is that this interconnection network is over-provisioned in essence, and that you use all the paths available by splitting the packets over them in a kind of round-robin way, in order that there's no congestion at this level. And that seems a reasonable assumption, although it does cost a lot of interconnection network. But that's their assumptions. Therefore, there's only congestion at this level and at this level. And they're proposing to implement schedulers, therefore, in the server, for the traffic going out of the server, and in the top-of-rack switch for traffic coming down to this rack of switches. And the particular scheduling they're using is not fair scheduling. It's shortest remaining processing time scheduling. So this is a size-based scheduling scheme, and it's known, it's fairly easy to understand that if you've got a set of jobs which are waiting, then if you want to minimize the completion time, the average completion time of these jobs, you're going to serve first the short one, then the second shortest one, and then the longest one. So this one just waits nothing, this one waits this time, this one waits this time. And that's a scheduling problem, a classical scheduling problem for jobs that you have all present at time 0. In a network, you're going to have jobs which arrive according to some random process as different activity takes place. And again, we know that shortest remaining processing time first scheduling is optimal for flow completion time. So you have to interrupt flows. This green flow was happy transmitting, and then the short guy came and it gets pushed out and it comes back into service after a while. So the protocols, the transmission protocols, transport protocols, have to be able to deal with this kind of interruption, but that's not too difficult. So this is what they're proposing. And the rate control, which will replace the TCP, AIMD protocols, is something rudimentary. It's not replacing, it's actually using additive increase, multiplicative decrease, the sawtooth effect. But you can do that in a kind of a crude way. There's no imperative to do that in a very friendly way, very optimal way, reacting to the AQM and whatever. This is something robust. And this is very interesting. Just a word about how they do it, because they've actually implemented this kind of scheduling in equipment, in the test bed in Stanford. You again have a shared pool of RAM and some queue logic. And the queue logic is different to fair queuing. The idea is that when you have a packet arrival, put it in the RAM and put a pointer to it into a FIFO list of packets in this part of the queue logic. So that's easy. On DQ, you're going to look for the packet in all this list that has the lowest priority. I didn't mention that the priority is marked in the packet and it's the remaining flow size to which that packet belongs. So that you can find that the latest packet of red has the shortest time. It's the shortest job. And this is the last packet to arrive. Therefore, it's the packet which is highest priority. But if you serve that packet, then this first packet here, which has got a longer remaining time because it arrived earlier, will stay there forever, perhaps, or for a long time. So the idea is that you identify the flow with the highest priority, and then you serve the packet of that flow, which is highest in the queue. So they've done that. It's interesting to know that they've done that, and they've done experiments and stuff, what people do in SIGCOMM papers, and they prove that it's okay. And it's interesting to note that the complexity of this thing, without doing any analysis really, but it's just, I'd like to convince you, or I'd like you to share my assumption or conviction that this is no more complicated than to do fair queuing. Because I'm going to propose, instead of doing that, you should do in fair queuing. So that was the recent work on AQM congestion control, which makes me think that the ideas that I've been promoting for maybe 10, 12, or even more years with colleagues is still very relevant. And it's very frustrating that people just don't seem to be taking it into account. So this is why I tend to talk about it like I'm doing now. So what's the case for fair queuing? First of all, TCP saved the internet from congestion collapse. This is a folk belief that Van Jacobson came on his big white stallion and introduced congestion avoidance. And from then on, the internet has gone on from strength to strength. And if we didn't have TCP, goodness me, what would happen to the network? It'd all fall into little pieces. The idea was, at that time, of the congestion collapse idea, was that you've got some flows coming through the network, and this orange flow happens to go through a link with a lot of congestion. And therefore, that if you don't have any congestion control, you can send packets at a very high rate, they're going to go through links which are upstream of this bottleneck and squeeze out packets of another flow. So that was the notion of congestion collapse, which was developed by Sally Floyd and others. And the idea is that with TCP, with congestion avoidance, you're going to reduce the rate here to the rate of the bottleneck, and therefore leave capacity for the other flows which can use it. That's basically what I've read about congestion collapse. It's not a very big phenomenon. It's a very difficult phenomenon to understand. And I believe you don't need to have everybody implementing TCP to realize that. You can do like in pFabric in the data center, have some rudimentary rate control which reacts to congestion signals, but not in a very precise way. Second thing, new TCP versions have been recognized as necessary for a long time now, high-speed TCP and whatever, but they're not, and they're still not, really very nice to legacy TCP. And if you put them together, typically the legacy TCP gets beaten up and doesn't get the rate, doesn't get the acceleration to convergent rate in any sense. There's obviously no incentive in the internet for users to actually implement a TCP-friendly congestion control, except that maybe you don't know how to do better, you've bought a PC and then the PC decides what you do. But it's fairly fragile from my point of view. If you want a worldwide network, which is so important, relying on everybody with his own little PC doing something which is compatible. Congestion pricing was a proposal, but, well, we'll not go into that. I think it's better, like pFabric, to decouple scheduling and rate control. But rather than SRPT, I think we should just do fairness. And fairness seems to be preferable, and I'll try and convince you that. Excuse me. An advantage of fairness is this notion of implicit service differentiation, in that any flow, like these blue flows, which emit packets at a rate which is less than the current fair rate, max-min fair rate, will suffer negligible loss, no loss, in fact, because they're nice within the rate which is imposed, and their delay will be very small because it will be determined by the number of flows they're in competition with, which is typically small, which I'll, again, illustrate later. This notion was introduced in FQ Codel that you can recognize in the scheduler packets coming from flows at low rate because they typically come in when they've no other partner already in the queue. That's the definition of low rate. And therefore you can recognize and distinguish from the other flows and give them priority and push them to the head of the queue. So we proposed that, and it's been reinvented in FQ Codel. And obviously this is not a new idea. This was first proposed in the early days of the internet by John Nagle, and he was dealing with congestion collapse, and he said, wouldn't it be a great idea to do round robin? And that longest queue drop as well, obviously, is necessary. And he said that as long ago as 1985 in one of the early RFCs. And it spurred quite a lot of research on different fair queuing algorithms, but it's never been actually implemented in any systematic way. The second reference I'm citing is from Vijay Kumar, Lakshman, Styliadis, others, which were designing PacketStar. So people from Bell Labs will recognize that was a Bell Labs invented router which did fair queuing natively. And they recognized that this was a great idea, but unfortunately Alcatel decided to buy some other crummy router and drop PacketStar. And this paper is from me and my colleagues, where we proposed this new flows priority idea, just to remind you of that. Google, who's done FQ Codel, are quite proud of the fact that they didn't take a patent out on this, and they said it's open, use it. But we did, unfortunately, we did take a patent. France Telecom took a patent on this. So the reason for my proposing this fair queuing, flow-aware networking arose from modeling traffic and trying to understand how the performance of the network depends on the traffic characteristics. So it's about modeling traffic at flow level. So rather than modeling traffic as a process of arrival of packets which you have to deal with, it's better to recognize that these packets belong to flows and that the arrival process of the packets within a flow is largely determined by things like TCP, or which in turn reacts to what congestion is encountered by the flow in question, what flows it's sharing the links with. So we're thinking about traffic in terms of flows, which can be identified more or less by header fields. And the flows in the network are obviously of different types. They have different voice over IP flows, TCP data flows, streaming flows with or without bursts. And they typically have different requirements. But rather than trying to detail all that, I tend to realize that their main characteristic is very simple. And it's what we call the peak rate. So here we've got a depiction of a video stream. This is packets arriving in a short time interval. I don't know what interval it was, but obviously it varies very much. And the TCP data varies similarly. These are typically self-similar variations, but that's not very important. And we're going to characterize them by ignoring these variations within the flow and assuming we can represent the flow by a constant rate. This is for the sake of simplicity. We'll think about flows as being constant rate, having a constant peak rate, but the considerations we develop should apply without any dramatic consequences to the real process of arrival. What's important is distinguishing the different peak rates of flow. So this is like representing a TCP flow which has not got a very high limit. The peak rate is typically determined by the rate at which you access the network, for example. And this might be a TCP flow coming from one server in a data center to another, or from one data center to another data center through the internet. And this would be a flow coming from your home, from your DSL connection, which can hardly get more than a few megabits per second. So the idea is that we're going to multiplex flows represented by these rectangles. The volume of the rectangle, the area of the rectangle represents the size of the flow in bits, and the height of the rectangle represents its rate, and the duration is the length of the rectangle. And with respect to this vision of traffic, we can identify different bandwidth sharing regimes. So we're thinking of a link in the network shared by flows occurring at random intervals according to a stochastic process with particular characteristics. And the first regime, which are called transparent, is a regime where all the flows have got a relatively short, small peak rate. This is typical of the internet. And the internet's got like 10 gigabit per second links and more. And the flows which it's carrying are coming from users like us who've got an access which is typically less than a few tens of megabits if we're lucky. So that's a very small fraction of the 10 gigabits which is available on this core link, this core or aggregation links. So the regime is such that the sum of these rates at any instant is going to be within the capacity. And that means that there's really no congestion whatsoever. There's no need to do anything. FIFO queuing is fine. And that's why the internet works, incidentally, because we're in that regime. It's not very interesting otherwise. I mean, it is interesting, the model. What's more interesting is the elastic regime, where we assume that there are some flows, at least, which can saturate the link, which can saturate the residual rate left over from the others. So this will be the regime typical of the data center, typical also of the bufferbloat case, because the link is short, smaller, because it's your own access, and you've got flows which can saturate it. So in this regime, because some flows can saturate the link, you get into the bufferbloat regime where there can be a bad queue, and there's certainly a queue, and then the performance or the behavior of one of these fat flows can have a bad impact on the other flows. So we need to do something. Rely on TCP maybe, or do scheduling. And the last regime is an overload regime, which means that if I'd taken more time, I would have filled this pipe completely with rectangles. The idea is that the arrival rate of flows per second multiplied by the size of the flow in bits, so that gives me a bit rate. If that bit rate is greater than the capacity, it just won't go through, will it? I mean, it's just obvious. So what happens is that the rate of the flows is going to have to be squeezed. There's lots of packet losses and what. It's a lousy situation. So we've got to avoid it. It's not to be controlled. It's to be avoided by traffic engineering or some other more drastic idea, mechanisms, which I won't go into today. So given these regimes, I'm interested in characterizing the behavior of traffic, the performance you're going to get in terms of a mathematical model. In fact, I'm just going to show you some results of simulation. So it's it's a term we call statistical bandwidth sharing. It's strange for me, but this is not something which you find in most SIGCOMM papers. SIGCOMM papers don't deal with stochastic processes. They deal with, you've got n flows in progress plus 1, and what happens? You don't have a process where n is varying all the time because flows are arriving and flows are ceasing, which is a very short-sighted vision of traffic, short-sighted vision of the traffic in the internet. You introduced this notion of load. I mentioned just now in the overload regime, overload means the load is greater than the capacity, which means the offered load, which is the arrival rate times the size divided by the capacity, would be greater than 1. That's just another way of expressing this load. It's the packet arrival rate times the mean packet size divided by the link rate. It's also the mean link utilization. So this is a parameter which determines to a large extent the performance of the network. If the load is light, over provisioned network, you don't have any problems. If the load is over the link capacity, you've got serious problems. In between, maybe you need to manage the sharing. Representing the traffic, we know that internet traffic has these typical day-to-day variations within a day. And the idea when we're talking about a load, we're talking about the worst load, the load in the busiest period. So we assume that this load here, in this busy period, maybe in the evening or whatever, is represented by a stochastic process, a stationary stochastic process, which means that you forget about these variations. You assume, for the purpose of modeling performance in this busy period, that the traffic was at a constant intensity forever. And therefore you get average measures for this process, this stationary process, and you assume that these stationary measures are appropriate for the performance in the busiest period, knowing that in the periods which are less busy, the performance is better. So you don't need to worry about that either. And the process of these arrivals might be very complicated. This is a kind of a self-similar process, but it doesn't really matter as I'll try and show. So we have this notion of a link between two things, might be between servers, might be between routers, might be between data centers. And we're interested in understanding performance. So we're going to do this by simulation. We can model it mathematically, but it seemed to me easier, especially when I presented this in another context, just to show simulation results. So we're assuming, for simplicity, that flows arrive as a Poisson process, and that the size of the flows has got an exponential distribution. And that when n flows are in progress, they each get 1/n of the bandwidth. And when n changes, it changes instantly. You don't need to worry about adjusting. So this is a model. Huh? And we've assumed these Markovian type of assumptions, Poisson exponential, for the sake of simplicity. It allows us to do simulations using a Markovian model in a very simple way. But as I'll say later, where I won't demonstrate, that the results we obtain with these simple assumptions are very generally applicable. And these are the simulation results. So I'm going to explain what I'm showing on this picture. We've got a load of 40%. This means that the average load on the link is only 40% of the link capacity. I'm showing on this graph the number of active flows. So this is the number of flows which are actually transmitting at some time. So this is a randomly varying process. At a load of 40%, you don't get very more than 5 flows in progress. The squares here represent the flows going through the link. And the key is that the flow is represented by a rectangle. This is the result of the sharing, not the input, as it was earlier. And the rectangle represents the mean rate at which that flow was transmitted. So 1 over this will give you the completion time of the flow, if you like. And obviously the size of the flow is, the length of the rectangle is the duration, because it's conservation of bits. We've got the duration times the mean rate equals the size of the flow. So here we're depicting flows. A lot of the flows arrive and are transmitted very rapidly without any interference from anyone else. Sometimes there are a few, 2 or 3 flows in progress, in which case the flows have to reduce their rate. And we can represent the result, at least one result, on a graph. We've got the relative throughput, the relative average size of these rectangles, average height of the rectangles relative to the link rate with respect to the load. So the load is 40%, and here we can observe that this is about at this level. And if we increase the load, then we get somewhat more fluctuation. The flows get a little bit squeezed. If we go a little higher, get more of the same. If we go to 90%, the rectangles are getting very flat. The number of flows, nevertheless, is still less than 30 on this particular realization, so it's still fairly manageable. And only if we want to saturate the link, go to 100% load, this is not a good idea. This is a queuing system which is unstable, and the number of flows in progress takes long promenades, long trajectories, and the average is typically not finite. So the graph here, which we completed, is a straight line. And if anyone's done any queuing theory, you recognize that this is the model I'm simulating is a processor sharing system. We're sharing the link bandwidth as jobs in the processing system share the CPU. And the performance of a processor sharing system is extremely well known. And in particular, the throughput, this throughput curve is a straight line, and the throughput at load is 1 minus load relative to the link capacity. So it's an extremely nice, simple result. And what's interesting is that for this type of traffic, this is kind of data center traffic, assuming this particular traffic model, we've demonstrated that the number of flows that you need to take count of in the SRPT scheduler or in a round-robin scheduler is small, relatively small, as long as the link load is not close to saturation, which is something you'd want to do anyway. I claim that that means that scheduling is feasible. This is just a flash of the reason why the results we've shown for this simple Markovian model are much more generally applicable. And this is because we can situate the sharing mechanism in a queuing network, as was studied in the 70s and 80s. And we know lots of insensibility results that the mean performance, this 1 minus load performance, don't depend on the distributions of the traffic. Okay, so that's not something I'm going to spend much time. Some more simulations. We talked about the traffic which was able to saturate the link. One flow was able to use the entire bandwidth. That might be true in a data center. We'd like to believe it is, that the servers can emit packets at 10 gigabits per second. It's possibly true. But in the internet, that's not true. So most flows in the internet have got a small peak rate, which is determined by their access. Might be determined by a modem, but typically by the access. They just can't use more than 1% or even 1 per thousandth or even less of the link bandwidth. So in this case, we're assuming we've got these flows. They're represented here by very flat rectangles. In fact, they're just lines. And we're representing on this graph, in addition to the number of active flows, the number of flows in progress. And it's important to distinguish the two. A flow in progress is a flow which is emitting packets. So it's a voice call emitting packets, 64 kilobits per second. But the active flow are the flows which have at least one packet in the queue. So most of the time, these very low rate flows, relatively very low rate flows, are emitting a packet, and most of the time, they're not. They're between packets. So there's nothing the scheduler needs to do with those flows. You only need to schedule packets when they arrive. So the number of active flows is a measure of the work that the scheduler, SRPT or round robin, would need to do. And again, we can represent that on a graph. The throughput is now determined by the peak rate, and it will be still determined by the peak rate as we increase the load to 60%, to 80%, and only when we get past the capacity will we get a reduction in this rate. There's still the same overload phenomenon. If we go into the overload regime, because the demand is greater than the capacity, things don't work. And the number of flows is still fairly well controlled, even at load of 90%. More typically, we would have a stream rate which is much less than 1%, in which case this would be more stable, but I'm not going to show that. So the observation is just the same as I did before, that most flows are not elastic, but even then, even though the number of flows in progress can be very big, hundreds of thousands are measured typically on backbone links, the number of active flows, the number of flows which have at least one packet in the queue is again very manageable. It's like the number of packets in an MD1 queue or MG1 queue at that load. So I conclude it's still, fair queuing would still be scalable, still feasible, not useful, because we're in the transparent regime. It's not useful, but if you've got this type of traffic is not going to stress the mechanism if you've already implemented it, because you might be in an elastic regime. So yet more simulations. Just now we're just going to mix the two types of traffic. Some traffic will be low rate. 50% of the traffic is just low rate, 1% of the link bandwidth, and the rest is composed of elastic flows, data flows. And the idea here is we just still got the number of flows in progress. We've got the number of active flows. So it's the flows of this type, we will have one packet in the queue. The flows of this type always have packets in the queue. That's the job of the transport protocol. But the number of flows in progress, the number of active flows remains stable. Even in this superposition. I don't know if you might have thought it didn't, but it doesn't. And yeah, this graph shows that you still have more or less, it's not entirely accurate, as pure as the process sharing result, but we can typically approximate the throughput of the elastic flows by this straight line, and the throughput of the other flows is unimpeded until you get close to saturation. So again, it's still feasible and scalable, and the notion of implicit service differentiation is illustrated by these results, because we see that the time a packet of the green flows waits is at most the number of flows in the queue. There's like a cycle of around all the flows, and you might wait a full cycle if you just arrive at the bad moment. But this number is less than 100, and 100 packets at 10 gigabits per second is like a few tens or 100 microseconds, so it's really nothing, no latency. Now, so I've talked about fairness, and I'm claiming fairness is a good thing. Now I'm going to claim it's all you need, that it's sufficient. And now I'm going to go through slides probably much more quickly than I ought to, but in the question of time. So first thing, when people do fairness and fair queuing, they're not content usually to do just pure fairness, where every flow has got the same share. They want to introduce weights, because weights can do QoS and stuff like that. Well, I'd like to claim that using weights is not a very good idea. It's complicated to do so, because the weight needs to be stored somewhere. You either need it in your packet header, or you need some state per packet, which is complicated. You don't just need to deal with active flows, you need to deal with flows in progress, which can be very big. So that's costly. And what I'm showing here is the throughput. Remember, this straight line was the result you get by a process sharing model when you get exactly fair shares. If here you've got a class 1, which is priority traffic, class 2, which is less priority, and we're assuming that class 1 gets 10 times as much bandwidth as class 2 when they're together, when they're competing at the same time for the same bandwidth. And you might expect, and people I believe expect, that you get 10 times better performance for class 1 than you do for class 2. But if you take account of this random process, the fact that sometimes the link is empty and sometimes the link has only got class 2 packets, and when it's got class 1 packets, it serves them very quickly and they get out of the way, and therefore you spend a lot of time serving class 2. In fact, in practice, the difference between the two is very, very much less than 10 to 1. And we get like maybe 2 to 1 at a load of 60%, which is not what was not the effect which I think is expected. So I don't think it's worth a candle. It's not worth the effort. And it's also an indication that if you don't do perfect fairness, if your algorithm is not perfectly fair, as some people would like to implement the wide sense fair, weighted fair queuing and whatever, that's nonsense. You really don't need to be so fair. You can do it approximately. You can maybe invent something which is even more efficient than a round robin. I don't know if it's the case. The second thing is this size-based scheduling. So PFabric introduced this, and this is seen to be a great idea, but it's not such a great idea, at least in their application. I think they're dealing with Facebook or Google, and it's a private data center where everyone can behave, needs to behave, but in a real network, at least in a network like the internet, there's nothing which would prevent a user from cutting up a big flow in little flows and getting better performance. So it's very easy to cheat. That's the first drawback. The second drawback is more subtle, is that SRPT is optimal on a single resource. That was the result I quoted earlier. But if you've got SRPT on a network, the performance is much less obvious. The problem is that you might be giving priority to flows which have got a short path because they happen to be the short flows. And this means that the big guy, the long flow, tends to be starved of resources if either of these two links is occupied. So this tends to lead to a loss of capacity. And well, this was studied by Maaike Verloop and Semborst. This is a thesis of Maaike, and they confirmed that SRPT in a network is not a very good idea. And Laurent and Thomas had also noted that a long time ago. In the data center network, we don't have a line network, but we've got a star, and I believe you get a similar kind of phenomenon. I don't know how to analyze it. It would be interesting to do so. This was an open problem posed by Maaike at the time. What's the performance of SRPT in the star network? And I think you get a similar loss of capacity. So that's not such a good idea. On the other hand, if you do fairness, if you realize fairness even using TCP or some better TCP, if you could do that, then it's been proved that this is stable as long as the load on every link in the network is less than 1. So it's a very simple stability condition. It defines the traffic capacity. You don't have a loss of capacity as you did in SRPT. And if you apply fairness, paper on Law of the Jungle by Thomas with Mathieu Feilly, Alexandre Proutière, showed that the throughput, no, the capacity is maximal whatever you do, even if you're extremely greedy. If you're extremely greedy, you get that congestion collapse phenomenon, which will reduce the throughput typically at lower load, but you still get the capacity, and that may be sufficient. But typically, obviously, you wouldn't be greedy as assumed in the congestion collapse work, that you typically use some rate control as in PFabric, which is rudimentary but sufficiently robust. A last argument in favor of fairness is that fairness allows you to engineer the network to required performance using simple tools. Tools as simple as the Erlang formula for the internet. And this has been my holy grail, if you like, for my career. I started working on the telephone network, and I learned that the Erlang formula was essential for engineering the network. And then when I've been studying multi-service networks, it's always been a question of finding the equivalent to the Erlang formula. And I think the work which has been done by especially by Thomas and Alexandre and Laurent also contributed, and a few others, has opened has proved that there is an Erlang formula with the internet. And very quickly, I'll show you what I mean by that. So in a loss system, this is not the Erlang formula, it's a multi-rate extension to the Erlang formula. If you've got traffic of different peak rates, C, and different intensities, A, you can calculate the occupancy of a link in the transparent regime, if you like, using this simple relationship. And what's interesting is that when you go to a fair network, you get the same recurrence relations, exactly the same, except that you go a bit further. You take into account the fact that the number of flows or the number of units of link bandwidth can exceed the capacity. I can't explain more than that. It's just that I just wanted to say, look, it's the same, more or less. And in fact, we can get an Erlang formula. We can actually use the Erlang delay formula to determine a measure of performance. So the measure of performance in question is probability of congestion. The probability that on a link, the fair rate at any instant t is less than some rate c is the probability of congestion at rate c. And that's interesting that if you've got a streaming flow or a flow that you don't want to suffer any packet loss or delay, and then that flow has got a peak rate of c, this is the measure of performance you're interested in. And what's very interesting about this measure is that you can express it in terms of these parameters, simple parameters. You only got the overall load, offered load. You've got the overall capacity and the bit rate of the flow in question. So this is it's an inequality. It's not very tight, but it just does show that the performance of the internet, even though packets arrive in self-similar processes, even though flows arrive in self-similar processes, and these are very complicated, you can still get very simple formulas if you tackle it in the right way. If you perform fair queuing, that's a great idea, and also if you understand the traffic that way. So there's a paper by Tom and myself which you could find more clearer and more full explanation. So the recommendation is obviously do fair queuing. Why don't you do fair queuing, Alcatel? Don't think about fairness as something like, really you need to be perfectly fair. It's really important. It's not. It's just an expedient. It's something you can do. It's something easier to do than fair SRPT, and it gives good performance. So why don't you? Applied traffic engineering, obviously, if the load you offer to a link gets greater than 1, you're really in trouble. If it's close to 1, it's not very good either. So do traffic engineering, make sure that the load is less than 90%, say, and have some mechanisms to be invented to deal with overload if it occurs because of a breakdown and all traffic comes over or something. But I'm sorry, I'm going to do this last bit quickly. This, I claim, is fine for the core of the network. It's not very good at the access. So we needed something else at the access in the last mile. I've just got 3 slides. So the last mile is between your home and the edge router, right, in a simple way, forgetting about DSLAMs and stuff. And you need to carry traffic from the internet, and you more and more need to upload traffic into the internet. AQM and congestion control, that's the CODEL, that's PIE, plus some clever TCP, congestion control, or flow-away scheduling. Simple fairness, as I've been advocating up to now, is not sufficient, because on this low-capacity link, you might want to use more than 50% for a video streaming and share the rest more or less fairly between uploads and downloads or whatever. So it's not simple fairness. You wouldn't want to cut down the video bit rate because you've got some background download. And who decides how you deal with this? I mean, currently it's typically the network operator, Orange or Free, will decide what scheduling you do and what services get priority. I tend to believe, especially since I left Orange, that it's the user should decide. It doesn't make sense. So sharing the first mile, this is from your home router. This is what bufferbloat can deal with. And I should say in defense of the bufferbloat people is that they're not just advocating FQ codal and that's it. They're actually imagining classes of service and doing FQ on each class. So there's lots of complicated things they can do. So it's in your home, so why shouldn't you or someone you trust be able to do the sharing? So that seems not out of the domain of reasonableness, and you may have particular priority considerations. I mean, you might be in a family and you might want to make sure you're paying for the bill, so your flow should get priority, and your kids using the internet, maybe you'd like to just limit his maximum rate. With all sorts of things which you could imagine that you could possibly implement in one of these gateways. So I don't believe they do that yet, but maybe they should. On the down link, the last mile, then you don't have access here. So it's not your equipment, you don't buy it, it's the operator who's providing it. But why don't they do the same thing? Why not implement the same type of mechanism? Obviously, it might be more complicated because you've got to implement a mechanism for each user. You've got sharing of these resources also between different users. But nevertheless, I believe that would be a development which would be very valuable, that if operators equip their edge routers with schedulers which allowed the user, by some form of signaling, to tell him, this is Dad's flow, give it priority. This is Junior's flows, he shouldn't get more than this bit rate, otherwise I may not be able to get my urgent, whatever. So that's a proposal, but nevertheless, to define exactly what that should do and how it should work, I'm not quite sure. We've thought about this for a long time. Jordan is not here today, but he's been working on this at some extent in his thesis. So in conclusion, AQM and congestion control, best a poor short-term solution, and then I don't think they are. I think that keeps a lot of people busy, but I don't think it's very useful. Rather perform fair queuing in the core, and that's got lots of virtues, as I try to convince you. And the last mile, it needs something more complicated, something which needs to include the user's particular requirements, so something flexible and sufficiently simple to implement. I'm not sure if those requirements are contradictory. So that's it. Thanks for your patience. Thomas?
Is it so easy to implement fair queuing in input queue packet switch? You have all the constraints.
Yeah, a long time ago I asked Nick McEwen if that was something we should think about, if we should think about doing, I mean, the thing I showed was output queuing. So your output is your RAM buffer, and you do that all on the output interface. Whereas in modern routers, the queuing is done on the incoming line card. What Nick told me at that time, he said, well, Cisco would just do a speed up. They do a speed up through the fabric, so there's no congestion. You get in the transparent regime through the fabric, and you only get to this elastic regime on the output. So you don't need to worry about it. So that's what he told me, and I didn't look at it ever since. I don't know if Alcatel will contradict me, but it's.
Just a comment. It is usually we do the scheduling. You have to output queues. It depends. Really depends on the speed up you have. The switching fabric to.
He talked of a speed of 2, so the maximum load is 50%. So 50%, and well.
And how does fairness relate to delay? In the sense,
Delay of what?
Delay of delivery of a service to.
Of a service, it's the response time.
Exactly.
So it's the throughput. The throughput is 1 over. I mean, it's inverse, the reciprocal of the speed up or slow down with respect to the link rate. So it's if you've got a link of 10 gigabits per second and it's loaded to 60%, the average throughput is 60% of 10 gigabits per second. No, it's 40%, sorry. It's the complement, 40% of 10 gigabits per second, which is 4 gigabits per second. So if you had that, it would be great, wouldn't it?
No, I'm just asking because in a sense, maybe because you squeeze somehow the flow of each flow is squeezed.
Yeah.
So you don't get 100%, you get 1 over n if you have n flows.
Yeah.
So in this sense, maybe you have certain, let's say, delays in finishing up the service, its service, right?
Well, that's what's translated in this average figure, this average throughput. So, I mean, the distribution of the throughput depends on the size of the jobs.
Now,
And
yes,
yeah.
I'm sorry to interrupt, yes, please.
No,
No,
well.
I just wanted to ask, like, if you put like a very hard like deadline, in the sense that I don't want to have more than delta t delay.
Mm-hmm.
Will you have to like cut off a number of flows that are shared within the link?
Well, it would be a very fat flow, very, very high speed flow, and I don't think that would be reasonable as an objective. I don't think that would be something which would be economically reasonable to offer as a service, frankly. I mean,
Why not?
but because it would be disruptive, it would give you a very small gain. Yeah, the gain is not worth the effort. That's what I mean. Yeah.
Yeah, I have a question about the home part. So you suppose that the congestion is on this last mile
Yeah.
link. I don't understand how can you apply this scheduling, fair scheduling, if you have flows that are based on TCP. So would you put a proxy before this bottleneck and then make a scheduling afterwards to simulate a link that is linked?
Well, you have a buffer here, you have scheduling here, you have scheduling here, and you implement a scheduler, which is what I said to be defined, but I mean it's a scheduler which will implement the objectives that you want to implement. Independently of TCP. I mean TCP, the only job TCP or the congestion control has is to keep packets in the buffer if you want the maximum throughput.
So still the users will see a TCP connection?
Well, you'd use a congestion control, like in pfabric, some rudimentary rate control, they call it, which, you know, be as much as, I mean, you've got trade-offs there too. You can be more or less aggressive. It doesn't affect the others, but it will affect your management. If you're aggressive and you send more packets than can be carried, you've got to keep them in memory so you can retransmit them, so you don't want to do that, probably. It's a trade-off, but it's for the network performance, you don't really care. The user equipment does what's good for its application. It can use high-speed TCP or it can use whatever.
I have a question again on the home router. I mean, a way to make it very simple would be hack the protocol, specifically TCP, and change the advertised windows to a rate that accommodates the non-TCP flows.
Well, that's what all these different types of TCP, I didn't mention it, but there's been work on LEDBAT, things like that, the lower than best effort type
you
of
could do it on the home
TCP.
router, right? Without
Yeah, and people, you can do that, but I mean, it's pretty fragile. If it's your home and you're sharing the link between your own flows, maybe you can trust yourself or trust the people in your... But that's, yeah, okay, maybe. But beyond that...
beyond that, I agree that...
I have a small question. With OpenFlow now, with the possibility to, I mean, really when we are over the load, could it be possible to have like a fair queuing, acknowledgement topology, or something that's at a certain...
You could implement admission control. Is that what you're thinking? Because, I mean, the number of flows in progress, we did a lot of work on that, and Jordan did in his thesis. The idea is that if you in overload, you recognize that by the fact that the number of flows, number of active flows is going to exceed 100, say. And if that happens, you say, wow, I'm in congestion, I better start getting rid of flows.
Because you have
so you,
that kind of...
Why? It will loop back.
It re-enter. I mean,
No.
it's waits around. It's kind of a loop back. It's stand in the queue instead of being pushed out in some other path.
Or you could do adaptive routing. You can imagine things like that. But yeah, that's a possibility. Yes, you could in OpenFlow. In fact, yes, in OpenFlow, I see what you mean. You could measure performance on a path, decide that that's getting too congested, and therefore do a reroute via another path. So that's something you could do, surely.
Because you have to.
But that's a different level. That's like traffic engineering anyway.
Yeah.
So it's the overload control aspect.
Sure, but you have to adapt to a certain capacity. And if you are in the core, you have big capacity, in edge, small capacity. So where the fairness is.
I think that's orthogonal to fairness. I think you'd still want to do fairness between the flows that you've allowed on that path, or allowed on each link of the path. At some stage, you recognize that there are too many candidate flows which are arriving. That won't work, because your schedule is going to seize up probably. So usually you do some preventive action by rerouting elsewhere. I don't know. That's a different problem. It's part of the traffic engineering problem, I guess. Yeah.
That incentive for being friendly, what do you gain with fair queuing?
Sorry, with what?
With being friendly.
With
when
being.
I generate traffic,
Yeah.
I use TCP because if there is congestion, I will reduce my traffic.
You do TCP also to recover from losses, so you still need that.
But I'm friendly with other work by using TCP.
I don't think it changes very much. If you've got a fair queuing scheduler, you can be friendly or not. You can be aggressive. Typically, you'd want to use AIMD, and maybe you should have an additive rate which is higher, multiplicative rate which is lower, and it'll work okay. Or
What
higher.
incentive do you get?
What advantage?
There's no incentive. Incentive.
There's no incentive. The incentive is you're managing your connection. So if you're more aggressive, you're going to lose more packets, and therefore you've got to retransmit them. Well, you've got to keep a memory of the packets. If you're cool, then your packets you just don't need to do much management. No pending packets.
Even with fair queuing, if I produce more packets, I will get more throughput.
No, no. As long as no, I mean, you might have a peak rate.
Active more often.
No, if
Users
you,
that reduce their flow. I will be more often active flow. My flow will be more often active. So
no, it won't be more often active. It'll be active all the time if it's got a sufficient rate to saturate the link. As long as it's got one packet in, it's the same as if you've got 100. So that won't change anything for anyone else. You're just going to keep serving that flow once every cycle, and that's all. But if you've got 100 queues waiting, that means you and your equipment, you've got to remember those 100 packets, which is a burden for you, and it's not necessary because it's not going to give you any more throughput. On the assumption that all the other flows are doing what they can to get the maximum throughput.
Philosophical question from data center. So, if it is really that easy with fair queuing, so why isn't the second community considering it at least as a comparison?
I don't know. I mean, they don't have the notion. I mean, I was thrilled by this Fabric paper because, I mean, there's someone who knows about queuing theory in that paper, Balaji Prabhakar. The others, not so much. But Balaji has introduced the notion of Poisson flow arrivals, okay? Which is, at least, you know, that's a reasonable idea. Whereas all the other papers on fairness, you've got n flows, different weights, but n doesn't change, and the weights don't change, and you just want to see how fair is it over an infinite horizon, which is unrealistic. So I mean, I don't understand why. I mean, they're allergic to queuing theory. I gave up submitting to SIGCOMM 10 years ago, and I submitted a paper, and I don't get it. So they didn't get any more of my stuff.
How come the router vendors don't seem to do that much of it either?
I don't know. I talked to Cisco at the time, and they're okay with it. I guess the reason is that they sell diff-serve, they sell weighted fair queuing, class-based weighted fair queuing. Operators buy it. They don't use it, but they buy it, and then they're very happy, and then they'll probably buy even Alcatel routers, doing very complicated schedulers, but not per flow schedulers. Yes?
I just want to make the comment.
Yeah.
In fact, what you need also is to convince operators that they need fair queuing.
Yeah, but I convinced...
They're asking us some features, and if you do not propose these features, then you are out of the market. So,
yeah, but we did. I convinced my director, the research director, Pascal Vigigny. He was keen on the idea. He went to, when he met Alcatel or Cisco, he talked about it, but we didn't get anywhere. I mean, there's been other examples where we tried to get some clever, intelligent mechanisms implemented. It's just too hard. It just didn't work. You need maybe Van Jacobson. He's going to say, this is an all across-the-board win, and everyone will say, oh, yeah, Van said, therefore. And actually, it's interesting. I don't know if it's true. I think it's true. Somebody told me that Van, who's now with Google, is actually implementing fair queuing, probably FQ Codel, in the switches in the Google data centers. So that would be interesting to have confirmation. But I mean, that's the kind of thing you need. I mean, if Google does that, and if they do that, and I think they're very clever to do that, and if people know, then they'll say, wow, Google's done that, we should do it. And Alcatel will come along and well, I don't know what Alcatel would do.
Personally, so you know that I work on some systems a bit different from routers, but mixing TDM switching and packet switching. And there were some requirements that were asked because in the product lines they had these requirements from, they said their customers, and so it was compulsory to have these features, even if the users, our customers.
Yeah, I know. The ecosystem is very complicated. It's very difficult. As I said, I went to Google, I went to California and made a talk and stuff like that. They were interested, but well, even they explained that even within the company, they want to get something implemented. It's virtually impossible. I mean, they're making a huge amount of money just selling what they've got. Why should they change? Why should they say, oh, what we're doing has been wrong for the last 20 years? They can't. And the operators can't say that either. They're doing diff-serve and says, it's great. Come. So, I mean, this data centers maybe the solution. Maybe data centers is much more dynamic and Google in particular, they've got the their operators and equipmenters. They do the equipment.
Okay.
Thank you.